Continuing on with finding the inverse of a matrix. So we've learned why we need it, because we know that we have to multiply a matrix by something to give us our identity matrix. We know how to verify it. We've got to multiply it in both formats to come up with the identity matrix. And we know how to do it if it is easy enough that we can set it up in this format. But most of our examples will not be able to do it in this format. So let's figure out how to find the inverse of a matrix very specifically. So I've outlined the steps for you here. They're really basic. We actually already know the principle behind this. We just need to take the actual time to get it done. So the way that we do it is we set up a row reduced or kind of an augmented matrix. The way we set it up is with our matrix on the left and with the identity matrix on the right. So this example was a 2 by 2, so we need to set it up with a 2 by 2. Then you row reduce it, or Gaussian elimination or Gauss-Jordan elimination, all the same thing, just different wording. Row reduce this so that you have the identity here on the left. And whatever you come up with over here is going to be your inverse matrix. So you've already done this when you solve system equations back in a couple of previous sections. We're doing the same thing again, except for instead of having the answers over here, we have the identity matrix over here. Okay, so you already know this process. I suggest that you pause the video and see if you can come up with this inverse matrix on your own. All right, well, in this one, the very first thing that we most likely want to do is get a 1 where this 4 is. So the easiest way to do that is to take row 1 divided by 4 and put it back into row 1. Now that's going to give us some fractions, and a lot of times when you're doing inverse matrices, you're going to come up with fractions, and there's no way around it. So that's a 1, a 1/2, a 1/4, and a 0. And then my second row stays the same. Okay, then we want a 0 where this 3 is. So I take my row 1 times a -3 and add it to row 2, and I'm going to replace it in row 2. If you need to do some scratch work because you can't do a whole bunch of simple math in your head, go ahead and do that. I'm one of those people. So I'm going to multiply my row 1 times -3 up here. So this gives me a -3/2, a -3/4, and a 0. And so I'm going to be adding these two rows. So my row 1 stays the same. Okay, and then when I add these, -3 plus 3 gives me 0. -1½ plus 1 gives me -1/2. -3/4 plus 0 gives me -3/4, and 0 plus 1 gives me 1. All right. Now I want to take this guy and I want to make him a 1. So the easiest way to do that is to take row 2 times a -2. Replace that in row 2. So my row 1 stays the same. And this, 0 times -2 gives me 0. -1/2 times -2 gives me 1. -3/4 times -2. So my negatives would cancel out. This would give me a 2 in the denominator because this 2/4 reduces. And so that would give me 3/2. 1 times -2 gives me -2. So the last thing that I need to do is I need to get a 0 where that guy is. So I'm going to take row 2 times a -1/2 and add that to row 1 and replace it in row 1. So let me do my scratch work here, times it by -1/2. So this gives me -3/4. This gives me a +1. And then I'm going to be adding these two rows back into row 1. So it gives me 1, 0, 1/4 minus 3/4 gives me a negative 2/4 or a negative 1/2. 0 plus 1 is 0. And then my row 2 stays the same. So I have my identity matrix over here on the left, which means with whatever I came up with over here on the right is my inverse function. So my inverse function, if I've done all my math correctly, is negative 1/2, 1, 3/4, and negative 2. So you can confirm this a couple of ways, is you can multiply your A times your A inverse to confirm that you get your I. And of course you have to do it the opposite way, A inverse times A, to confirm that you get the same I. Or in the last video in this section, I'm going to be showing you how to double check this by using your graphing calculator. Okay, let's do this again. But let's do it with this matrix here. Matrix B equals 0, 1, 0, 0. So if I were to set this up, I have my matrix B on the left, and I need to set it up to have my identity matrix here on the right. So if I tried to re-row reduce this, notice we wouldn't really get very far because I would want to create a 1 here, and there's actually no possible way to create a 1 there. So I actually cannot row reduce this. Row reduce echelon format this guy. Well, if I cannot row reduce it, that means there actually is no inverse. And if you don't believe it that way, then we can set it up the first way that we set it up on the first video, where we set it up here, and then if I multiplied it by another matrix to get my identity matrix, I would notice the same thing, that I wouldn't get very far. A 0A plus a 1C has to equal 1. A 0B plus a 1D has to equal 0. A 0A plus a 0C has to equal 0. And a 0B plus a 0D has to equal 1. And in this last equation is where I really come up with an issue, because there's nothing that I can plug in for B and D that gives us 1. So there is no inverse for this. So the thing to note with this example here is that not all matrices do have inverse. So not all matrices have inverses. Now we know this one is really unique because there's lots of zeros in there, but there's other examples that don't have inverses. The one thing that we do know right off the bat is a matrix has to be square to have an inverse. So something guaranteed is a non-square matrix absolutely has no inverse. So if you look at the examples that we've done so far, this one in the first video was a 2 by 2. The first example here was also a 2 by 2, a square matrix. So these ones are definitely square. If you ever try and take the inverse of something that's not a square matrix, guaranteed you're not going to come up with a inverse because there is no formal identity matrix to come up with it. Remember, all identity matrices have to be square matrices as well. Okay, this is where I'm going to stop this video, and I'll come back and we'll work some more examples of finding inverses and what do we actually utilize them for.